Right, so today, what if clouds could be more reflective? And this is really part of our Centre for Climate Repair. How do we cool the planet, get off fossil fuels, of course, CO2 and methane out of the atmosphere, of course, but reflecting sunlight, well, of course. Anyway, that's what we're talking about today. Dante McGrath is a postdoc in the Centre for Climate Repair. He did his PhD on droplet generation inside diesel engines, trying to make the fuel burn more efficiently. And he's turned that work around. Instead of being on the side of generating greenhouse gases, it's on the side of dealing with the problem. So Dante, I'm going to hand over to you.
Thank you, Hugh. Okay, yeah, thanks, Hugh, and hello, everyone. I'd like to introduce my research to you today with today's what if. What if clouds could be more reflective? So before we get to that, I want to address two other questions. How do clouds form, and why do clouds matter? So clouds rely on the following processes: saturation, cooling, and condensation. Now, I'm a very keen baker, and that's relevant, I swear, because I like to think of things in terms of ingredients for a recipe, and we can view these processes as ingredients for a cloud recipe. So here goes. We need saturated air, so air mixed with water vapor. We need that saturated air to rise and cool down. And like most recipes, we need a pinch of salt, or rather many tiny solid particles for the water vapor to condense onto to form droplets. And that gives you your cloud, a collection of droplets suspended in air. So why do clouds matter? Well, clouds affect climate. They affect climate in two ways. They contribute to the all-important water cycle, and all-important for today's seminar, they contribute to the Earth's radiation balance. So clouds can have both a cooling effect and a warming effect. They're capable of reflecting or trapping heat during the day and trapping heat at night like a duvet. So whether clouds warm or cool depend much on their position and their composition. Low clouds tend to have a cooling effect due to their thickness offering high reflectivity. High clouds, on the other hand, offer a warming effect due to their ability to absorb heat radiated from the Earth's surface at higher and therefore colder altitudes. Now, the cooling effect of clouds may well prove to be a vital defense against ecosystem collapse. Two ecosystems that are front lines of climate change are the Arctic and coral reefs. So we heard in the previous seminar the importance of Arctic sea ice as a means of regulating the Earth's temperature by reflecting sunlight back into space, much like low clouds. And they also regulate ocean currents as well. Now, since the late 70s to present day, we've seen a downwards trend in the extent of Arctic sea ice, both in area and in volume. Now, this weakens our natural barrier from global warming and threatens the lives and livelihoods of Arctic communities. Over a similar time period, but at much lower latitudes, scientists have been monitoring the Great Barrier Reef, which is off the coast, east coast of Australia, for signs of coral bleaching. The first mass bleaching events were recorded in 1998 and 2002. In both cases, most of the reefs basically achieved a near full recovery. But fast forward to the mid-2010s, and we started to see alarming trends, back-to-back mass bleaching events. And not only that, but also bleaching that was most severe at lower and lower latitudes with year on year. And unfortunately, this trend has continued into the current decade. Mass bleaching events recorded in 2022 and in 2024. And so coral bleaching poses a severe risk to marine biodiversity. Coral reefs are this cradle of life on Earth, and it's being decimated by the rising temperatures. So alarm bells are ringing, like the ones we're about to hear, from latitudes high and low. Ice is melting and coral is bleaching, both at alarming rates. In this seminar, in this state of affairs, we pose today's question, which is what if clouds could be more reflective? And it's this question that motivates the study of marine cloud brightening. Clouds at sea depend on seawater, and seawater carries salt. As waves crash at the surface, salt is carried into low clouds and become that final ingredient to trigger cloud droplet formation. Now, marine cloud brightening as a phenomenon mimics this process, but with a key distinction. Clouds with a large number of tiny droplets are brighter than clouds with a small number of large droplets. This is demonstrated in our last seminar, actually. So clouds can reflect heat provided they have enough salt particles to produce enough small droplets. Now, as it happens, human activity has already led to inadvertent marine cloud brightening, and we can see that from satellite images. Cloud formations that seem to match shipping tracks, and indeed, those clouds are brightened by the exhausts of ships. But rather than relying on bunker fuel to offset global warming, what if we could make clouds more reflective with a natural ingredient abundant at sea? And so marine cloud brightening as a concept involves the spraying of salt particles into low clouds to produce small droplets in vast quantities. And this could aid the cooling effect of low clouds, protecting Earth's ecosystems from sea ice to coral reefs. And so the aim of our research is to design a scalable and energy-efficient system to produce sprays to brighten clouds. And we have 5 key requirements. The droplets must be submicron, so less than a micrometer, to produce salt particles on the nanoscale. They must be fairly monodisperse and be produced at a rate of 10 to the 15 particles per second at least. And of course, the technology has to be scalable and energy efficient, such that we can translate lab-based observations into real-world impact in a sustainable and responsible manner. And so our centre is investigating 4 spray methods: twin fluid atomization, flash boiling, electrospray, and Rayleigh jet breakup. Now, all these methods serve the same purpose, trying to overcome the surface tension of water to induce atomization, so to convert a volume of liquid into a spray of droplets. So how do we atomize a liquid? We can blast it, impinging the liquid with high pressure gas. This forms bubbles, so those white dots you see on the slide, which grow and expand to produce or to break these liquid columns into small droplets. Last time that happened, it happened like just when I mentioned the word alarm bell, and it just is
Perfect.
not so today. We can boil it, injecting heated liquid through a nozzle to induce a phase change, and this too causes bubbles to grow and expand to break up liquid columns. We could charge it and establish a high electrical field at the tip of a micron-sized capillary. This produces high electrostatic forces that introduce a pressure to overcome the surface tension. Or we could vibrate it such that natural and induced perturbations grow and again break up liquid columns to produce fine, small droplets. So we already know have a rough idea of the pros and cons of each technique. The first 2 methods have great scale-up potential and high production rate, but they have a very broad size distribution, which can actually have a detrimental effect on cloud brightening. The other 2 methods, on the other hand, have highly monodispersed droplets and are less energy intensive, but they do have scale-up challenges. So consider that the first 2 methods produce ballistic sprays, while these 2 methods produce 1 droplet at a time per nozzle. So rather than requiring hundreds of nozzles of with millimeter-sized holes, you would require millions of nozzles with micron-sized holes. And that presents challenges that we're about to address in the next presentation. So those are the suite of methods we're investigating. And for each, we're developing a suite of measurements to compare their suitability for marine cloud brightening. It's the search for an energy efficient and scalable spray mechanism to make clouds more reflective. And in doing so, we could bolster society's toolkit to address the impacts of climate change, from ice melting to coral bleaching. Thank you.
So thank you, Dante. I don't know whether it's a coincidence, but both Dante and I hail from the southern continent, where the coral reefs are pretty significant part of our psyche. One of the things that we've really cottoned onto on our Centre for Climate Repair is the importance of engagement with local communities, and I think one of the things that is very true about the work that's going on in the Great Barrier Reef is how much the local Aboriginal communities have really engaged with the problem, as you know, we're trying to solve it from a technical point of view, but they're bringing to the table their own side of the story. And it's been a really encouraging thing. It's taken a couple of decades to develop, but it's important that we engage with Indigenous people. The engineering course here in Cambridge is a 4-year course. First year students start off not knowing whether they want to be mechanical, electrical, civil, whatever, engineers. In the second year, they begin to specialise a little bit. In the third year, they choose particular modules in whatever they might be, control systems or structural dynamics or whatever it might be. And then in the fourth year, they carry on to specialise, but they have to do a master's project. Master's project is worth roughly 50% of their marks, which means that during the year they study modules, have lecture courses, but that's about 50% of their marks. They also do a project where they have to develop their own ideas, do experiments, write reports, give presentations. Now, Orla Hill is a fourth year project student she's at Emmanuel College and has chosen to do her project in the Centre for Climate Repair on the particular issue of seawater filtering. And the reason this is important is that seawater is not as nice and simple as you might think, and we don't want to block up those nozzles. But I don't want to say everything that Orla's going to say, so over to you, Orla.
So my name is Orla Hill, and as you said, I'm a fourth year Master's Engineering diploma.
I can give you this one.
Oh wait, there we go, I think that's on. My name is Orla Hill, and I'm a fourth year Master's Engineering student with the Centre for Climate Repair. The focus of my project is on seawater filtration for marine cloud brightening. So as Dante spoke about, the Centre for Climate Repair is looking at various different options for implementing marine cloud brightening, which focus on 4 different methods of generating these very tiny droplets. All of these options have different benefits and different issues. One of the most promising ways that we're looking at generating the droplets has a very specific problem, which is that you are blasting raw seawater, so like what you would swim in at the beach, through 1.6 micron diameter holes. So that is about a 1,000th of a millimeter. It's very, very small. And as you know, seawater's got all sorts of random stuff in it. And you have to find a way to clean the water sufficiently so that it can fit through these nozzles without blocking it. And obviously this is an issue both in terms of actually implementing marine cloud brightening, but also in terms of assessing its usefulness as a solution to global warming. Because if we find that actually this technology requires you to update the nozzles after only spraying for a day because they've blocked up so quickly, you produce a lot of waste, and then the overall value of it as a sustainability solution decreases. So it forces you to kind of to think about this problem in a very kind of, on a large scale, you know, what's the whole life cycle of the solution? So my main question is, how do we spray raw seawater through 1 micron holes without blocking them? Which is quite simple. It's a pretty simple statement, but it's obviously more complicated than that. So first of all, I conduct a literature review. Understanding about filtration systems is not something that's taught explicitly at a university course. It's actually one of the big draws about doing master's research, I would say, is that you get to kind of deep dive into sort of an area that has a direct application. I learned all about how do you choose membranes, so things like the pore size, which is quite obvious, filtrate compatibility, so if you've got a corrosive solution that you're trying to filter, what kind of membrane do you need, what chemical does it need to be made of, hydrophobicity, which is how it interacts with water, basically, which is obviously crucial for this, and then fouling, which is about how quickly do those membranes basically get blocked up. And this all led me to ultrafiltration, which is just a fancy way of saying very small holes. So if you look at this diagram, which is from osmonics, you can see here in the 0.001 micron scale, you have aqueous salts. So obviously that's the sodium chloride that's in seawater, which crucially we want to keep in, because otherwise we don't produce the small salt crystals which increase the albedo of the clouds. And you can also see here we have the 1 micron area. So that is the size of the holes that we're trying to not block. And then you can see that in the middle here we have ultrafiltration. There's also microfiltration and nanofiltration, which just means, again, slightly different sized pores. It's a kind of popular rule of thumb in membrane technology that you want to filter to between 5 and 10 times smaller than your smallest hole in order to prevent blockage. So ultrafiltration is kind of a good place to start. As I talked about, you have to think about feasibility in terms of a whole, you know, implementation strategy. So seawater filtration is important for the method of droplet generation, which uses these 1.6 micron holes. And that means that the overall system of that droplet generation has to account for the energy requirement and the material use associated with filtering the water. So we do some kind of back-of-the-envelope calculations to assess feasibility before we dive into kind of deeper research. Essentially using examples of ultrafiltration systems which are used as pre-treatments for reverse osmosis plants, which are where you are typically used for desalinating seawater to produce drinking water. Using sort of basic standard values of flow rate and power requirements from those plants, we can make a kind of assessment. And crucially, what we come to is the effervescent spray method of droplet generation, which is kind of one of the most forefront examples of droplet generation being used in marine cloud brightening in Southern Cross University in Australia. They have a power requirement for 10 to the 14 droplets per second of about 150 kilowatts, which is when you try and scale it up to produce sort of 1.5 degrees, 1 degree of cooling, it's not very feasible. The Cambridge method of using these med spray nozzles is 15 kilowatts, so a whole order of magnitude smaller. And then we would have to add on the additional power requirement associated with the filtration, which is, using these calculations, about 7.5 kilowatts. So it's good, basically. It's not increasing the power requirement by a whole order of magnitude. And there's also reasons to suggest that this is kind of a worst case scenario. So hopefully it can be even better than that. So we continue our research because it's looking good. So my research is got a couple of kind of prongs. First of all, I have an experimental setup. I've acquired different membranes from different filter suppliers from Germany called Mann and Hummel, who have sent different filtration membranes which have different pore sizes. I have 20 microns, 0.2 microns, and a type of filter which has, it's characterized by the metric kilodaltons, which is to do with the molecular weight cutoff. So basically how heavy can a molecule be that won't be allowed through the filter. But it kind of relates to about a molecule of 0.1 to 10 microns. And then using these, I explore a combination of different processes, basically. So do I use the 20 micron filter first to screen out larger particles to prevent the fouling of these smaller, more specialized filters? Do I use the small ones first? Because actually, if you use a finer filter, you have less risk of damaging the filter because any really large particulate will just be blocked. Whereas if the filter is sort of a close size to the particulate, then the particulate matter can get embedded within the filtration system and the membrane and then actually ruin the membrane faster. So there's all kind of different things to consider. And then by taking pressure measurements, by considering how hard the suction has to be applied in order to continue to pull water through that membrane, you can assess how quickly the membrane is fouling. I'm also assessing how quickly the membrane is fouling and how effective the filtration is by using microscopy and computer vision, which is a software that has been developed with OpenCV. This is coded in Python, which I will talk about in a bit. And finally, I will assess the quality of the filtrate I've produced by actually spraying through the nozzles that we have got to kind of see how quickly they foul, and that can give us a more accurate understanding of the total life cycle of the system. So my microscopy analysis has consisted of collecting images, processing them using computer vision, as I said, counting the number of particles that are in each sample of filtrate, so that's both the raw seawater and then seawater that's been through different stages of filtration. And then you analyze the size of those particles and you can place them in bins, basically. So saying that this sample of seawater that's undergone this degree of filtration has this percentage of particle matter that is between 0.5 and 1 micron, for example. And then when we analyze how quickly that will clog the nozzles, we can understand what is the interaction between the filtrate quality and the damaging of the nozzles. So, for example, this is a picture that I took on the optical microscope that's in the Department of Raw Seawater. You can see there's very large particulate matter, 150 microns. And if you think that this has already been sort of filtered to some extent because the sample's been extracted with a pipette. So you wouldn't think of it necessarily as a filtration step, but actually, obviously, any blob that's too large to fit into the pipette wouldn't end up in the sample. So, there's already kind of a screening process that's going on there. Then I looked at examples of medical grade saline. So this is using a 5x objective lens. So the size of this is approximately 2 millimeters. So it's very zoomed in. And you can see that the particulate matter that is there is very small, kind of on the micron scale, which is obviously of particular interest for my research. And then using the computer imaging software, first of all, we apply, this is an example of a Gaussian filter. It's basically to reduce the noise in the image. And then we use what's called the canny edge finding algorithm, which basically analyzes the gradient of how quickly the value of the pixels in a photograph are changing. And how steep that gradient is will tell you if there is an edge there. Because if a gradient is quite shallow, the pixels are changing color quite slowly. It suggests that it's maybe like a shadow or it's general kind of modulation. Whereas if it's very rapid, then there could be an edge there. And it creates this binary image, which is just black and white pixels. So you can see when you switch between, obviously there are different images, but you've retained the crucial information of where the edges of the particulate. Then you use dilation and closing algorithms to basically increase the size of the edges that you've drawn, and in a sense that closes them off. And then this image can be used, you can use other algorithms to count the amount of white pixels, basically. And that will tell you how much particulate matter there is in a given sample. And then essentially you write this pretty simple code, and it can count the amount of particulates in a given image. And so by analysing a large amount of these images, we can sort of quantify the filtrate quality. So the next step is to kind of do this active placing each of the different particulate examples in different bins based on their size, and therefore allow me to relate that to the experimental setup that I have. Thank you, and then if you have any questions about this or you're interested in seeing the test bench, you can feel free to email me. Thanks very much.
Great, thank you, Orla. If anyone is interested in fourth year projects, then it's always good to talk to fourth year students about what they're doing. And Orla, happy to do that. Then there's other PhD students who are in the room happy to talk to you about the fourth year project as well. Now, our next speaker is Adam Boies. Adam he's from the US, Minneapolis, Minnesota. Is that roughly right?
Yeah, that's right. Yeah.
And was here in Cambridge for 10 or 15 years. Can't remember exactly how long.
Yep.
But as we've sad that he's now very good for you, Adam, that you've gone to not Caltech. What's it called?
A very startup university relative to Cambridge, Stanford.
Stanford.
Yes. Yeah.
So Adam is over in Stanford, but he's got a good relationship here with Cambridge and spends a few weeks here 2 or 3 times a year. We're very glad that he's here with us, just happens to be here this week.
Just for this. Yeah. Just for this. I came for this.
I just came. That's very kind of you. And Adam has worked a lot on sort of aerosols stuff during COVID. You were very busy looking at the aerosols in the COVID particles, looking at getting rid of pollution in Paddington Station, all those little particles.
Good memory. Yes. Yeah.
Well, there you go.
Yeah.
And then, but now you're going to tell us a little bit about aircraft and perhaps reflectivity of contrails.
Happy to. Yeah. Thank you
Great.
so much for having me. So I'll talk a little bit about kind of the evolution of at least our thinking of how aircraft emissions affect us, humanity, both from a health perspective and then from a climate perspective. So, I was born in 1979, so, this is what plane flights looked like, when I was born. And it was really a place you didn't want to live was near airports because of these large plumes. What happened is that regulatory limits came in effect in the 1980s, and were really concerned around the visibility of particles, and adopted a standard called smoke number that to the naked eye said, hey, this is a drastic improvement. In fact, no flight no plane has ever failed type approval since then. But that doesn't mean that there aren't emissions. In fact, the contrails you see in the atmosphere when a plane goes by is a result of nanoparticles serving as nucleation sources for water droplets. So there are definitely still particles in this stream. They're just much smaller than the wavelength of light and don't scatter much light then. I've got a set of slides here that I'm not going to talk much about, but just kind of the evolution. It's kind of interesting to know how this interplay between, say, engine design and specification largely interplay with the regulatory methods that are enforced. And so what happened is that a smoke number test fundamentally measures how black a filter gets. So it's just the reflectivity off of a quartz fiber filter. And because of that, of course, engine manufacturers, Rolls-Royce and others, responded to that and made particles smaller. Now, was that good or bad? We don't know. There are some benefits to that. Certainly, the mass concentrations went down dramatically. But if you look at what correlates to, say, contrails, it's not the amount of mass that you produce, it's the number of particles that you produce. So the metric is really important as well of what's regulated here. So I'm going to skip a few slides just to kind of jump to something that was actually really relevant to the last talk, which is how particles collect on a filter face. And this is very much to kind of what was being said before. It depends on the size of the particle. And so small particles will collect differently on filter faces than others. And I don't know if this has a, oh yeah, there is a laser. Again, there's some non-dimensional numbers here. So for those undergrads who are kind of taking some of these fluids courses, Stokes number is the stopping distance relative to the size of the particle. And you can see that for large Stokes numbers, you get kind of the particles all collecting on the top of what this cylinder here is kind of into the page would be one fiber. So you can think of it as one fiber in a filter, and that's what we're looking at. If you have, say, low Stokes numbers, or another metric would be Peckley number, which is again kind of a ratio of advection to diffusion, would be where particles maybe collect around, and they're primarily diffusion dominated in this case. And so you get as many particles on the back of the filter and thus don't scatter much light, right? Those particles, if you send a light beam in from the top, aren't measured by that light beam. So the size plays a big role, both in the way in which we collect things, as said before, and also the way in which we regulate these materials as well. So we came up with some estimates really to, it's one thing you might imagine, it's very hard to do measurements at altitude. So look at what are the actual emissions at altitude. And so those are a series of, there are chase studies. In fact, the UK has one of the best chase planes in the world for doing chase studies where you're flying one plane and then making measurements behind it. But the vast majority of data we have is actually measured emission indices. So EI is an emission indice, so it's the amount of mass per amount of fuel burned of black carbon. That's what, to decode that a little bit there. And we can measure that at ground, and then we'd like to estimate that at altitude, right? And that's the thing we'd like to populate for our climate models or our health models, whatever they might be. So we made some effort. A student of mine, Mark Stetler, who's really stayed in this field and has done a lot of great work on this about 10 years ago and is now a professor at Imperial College, is doing important work in this field. One of the effects that we were particularly interested back then, 10 years ago, was, well, what is the effect on climate of all of this? And so you can imagine that a small black particle absorbs radiation very well and would be net climate warming, right? So if you put lots of black things out into the atmosphere, you're going to have a warming effect. And so at that time, our models were sophisticated enough to kind of look at all of the flights in the world and kind of calculate what is the total amount of warming that one achieves from that. And it was much higher than what was being estimated in global models at the time. The big thing we were missing back then was what is the impact, what happens to those particles after they're emitted? So they don't just stay particles. In fact, few things stay just particles. And the whole point of marine cloud brightening is they grow droplets, right? Well, that's what happens, and that's what you see when you look up at a flight going by, is you see a contrail. You don't see the nanoparticles, you see the water droplets that have grown on this surface. These models didn't account for that, and that's where more work is needed. So if you look at this contrail to, in particular, what becomes really challenging is to not predict what just happens just at the exit plane of the plane or just downstream of that, but what's called persistent contrails that ultimately form high cirrus clouds. And those high-level cirrus clouds are what are called optically thin. So in other words, they let visible light through, so they don't scatter much or absorb much visible light, but they do happen to absorb and scatter well in the infrared. And that is exactly the greenhouse effect, right? And there is a relatively small but important fraction of airline flights, about 15%, that form persistent contrails. And those 15% of flights have as much impact as all the other flights CO2 combined. And so it's a huge radiative forcing from these flights. And of course, that's gotten a lot of people interested in how these form and what's going on here. So what happens at kind of a mechanistic level is that a soot particle is emitted. Actually, soot is hydrophobic. Water doesn't like to grow on it, but through a series of chemical processes that surface gets coated, water droplets do ultimately form, and then ice crystals, they freeze. So farther downstream, you actually get freezing processes, and then those either grow or evaporate or sublimate as that contrail matures into the atmosphere around it. And so it's incredibly hard to predict that from a couple of perspectives. So one thing we are not good at modeling yet is what this coating looks like on these really small particles here. So our models, climate models in general, not just contrail models, but climate models in general, started off by modeling aerosols as just little black spheres. Then we said, no, we know that water condenses on them, so let's put liquid on our sphere and just assume that everything is equal. Well, we kind of realized, no, actually, soot looks more like this, and then we think, well, we could grow a uniform coating on that, but actually what we see from electron microscope studies is that actually they're not uniform coatings. The liquid likes to go in certain spots more than it does others, and therefore, how should we model this is a question. So a student that's graduating from Cambridge right now in our group has really spent a lot of time looking at that in the early stages of water growth on these particles and how they evolve and where the water likes to go, and ultimately what forms a final state of those particles. And so there are interesting things. We did this both experimentally and numerically. And interesting things that happen along the way is that the particles actually restructure. So as the water comes in, you get these little capillary forces that collapse the particle down and change the structure. So it is the water is not just kind of a bystander in the structure. It's actually modifying the structure as it goes along. So that is important, again, for these climate models, where now, you can see we've got lots of data here from a lot of different studies, and we have models now that can more accurately predict that over a wider range of what's called mass ratio. So this would be like the mass of water that you've added relative to the mass of the particle that existed previously. And the optical properties then are kind of the next thing you'd like to know. So what we've done to answer that question is we've said, well, what happens if you put these particles into a system that would solve Maxwell's equations at a very discretized level? So you break the thing up and you solve a bunch of equations of how light interacts with matter, and you can look at what those optical properties are. So that's kind of one set of studies we're doing. And then another set of studies is to look at, well, how does water grow on this surface, particularly as it evolves from carbon, the thing that is in pencils, to a organic structure that often coats these particles, which is also kind of emitted from the plane, so kind of a soup of materials on the surface. And that plays a large role in what's called activation fraction. So the amount of particles that actually grow water droplets is different by a factor of 1,000. And so we are really bad, humanity, predicting which particles grow water droplets. And a factor of 1,000 difference is not something you would like to put into your climate models, because it has big impacts one way or the other. So one way to solve that is to kind of, again, look a little more at the surface as it evolves. And so what one can imagine is that you have solids, then you have, say, organic species. So these would be like alcohols or other sulfate species that occur on the surface. And that changes that surface interaction to water, and thus allows either water to grow better or more poorly, and has an impact on the ultimate contrail that forms and the climate impacts that it would have thereafter. So I think with that, I'll just kind of highlight, where does all this go? This, kind of, we in academia like to couple lots of models together and name them after the universities that we're a part of. So the CAM model, the Cambridge model, with the coding model. This is the discrete dipole approximation is just a way of saying how does light interact with these particles. And then these are these big global models run out of Switzerland, ETH Zurich in Switzerland, that we're feeding into to look at the climate impacts of these as a whole. And so with this, we think we've got a better representation now of how these particles grow, both in contrails and in more generally for climate models, and that allows us to say a little bit more what is the direct radiative forcing, in other words, the climate impact at very localized scales because of these types of effects. So with that, I'm happy to, conclude probably. I don't know, take questions. Yeah.
Great, well, thank you, Adam. I mean, I think where we're at now is that with clouds, the sort of simple understanding of clouds is that particles make these droplets. Hey, we can brighten the clouds. But then when you start to look closely, the closer you look, you realize, oh God, we have to filter this water to make this happen. And even if we do make it happen, it's not working quite the way we thought. And I like the idea that could we control where the planes fly, or how high they fly, or what we put in the fuel to make flying negative emissions? I bet you Boeing would like that. So what we want to do now is, there's any questions anyone might have. We've got about 10 minutes or so for questions, which is great. Love to have some questions from the Lee School students if they're interested in asking. I'd love to have questions from our own students. To Dante, to Orla, to Adam. Over to you. We've got a question up the back. Can you use the microphone because we're going to be...
Quick question to Adam, please. Can you talk to us about where the particles are coming from? Why they're coming out of the engine?
Yeah, it's just a natural byproduct of combustion. So with hydrocarbon fuels, the carbon and hydrocarbon, unfortunately, doesn't all turn, well, I mean, this might be kind of an oxymoron here, but that, you know, we would like in combustion process for it all to turn to CO2. I know from a climate change perspective, you would like to not have CO2, but as long as you have carbon in a fuel, you want to turn it to CO2, and the hydrogen you want to turn to water, but not all of that carbon goes to CO2. And so in particular in conditions like this where you have mixtures that are not always fully dispersed, fully well mixed, you get rich pockets of combustion that then ultimately result in carbon, and that's why you see it kind of at a campfire or something as well. You'll have spots where there's lots of fuel, very rich pockets, and those tend to not have as good a mixing with the oxidizer and thus don't produce CO2 and leave some behind in the form of carbon. Yeah.
Is there a trade-off that maybe you get more energy efficiency out of you, more thrust out of your engine if you've got a few particles left behind? And is it kind of, we'd rather have not...
I mean, yes, in certain cases, you know, in old sports cars, you'd run them. If you've seen a Corvette going by, you know, they might tune those a little bit rich so that they are, you know, you do smell the fumes coming out. But in general, most modern engines want to run at, you know, ideally perfect combustion. So they're turning everything into CO2 and water. They're just not able to do that fully. Yeah.
So other questions? We've got a question here. Yeah.
Is marine cloud brightening more effective in certain parts of the world than others, and why would this be if it is?
Yeah, short answer is yes. But the best places aren't always the places that need it. So in general, the best places have been found to be along the west coast of most continents. So west coast of Africa, for example. You're right. It does. There are certain areas that are more conducive to cloud brightening, and certain clouds that are more conducive, specifically stratocumulus clouds, which I like to think of as the Pixar clouds, the nice fluffy ones, low-lying, warm, offer that cooling effect because they have a high optical thickness.
So around the Great Barrier Reef, is that a good place for marine cloud brightening?
Good question. No. One thing it has in its favour is it's very clean air on the reef. And so with the field experiments that are being undertaken on the reef at the moment, they have a very good baseline, very clean, the cleanest air you could hope for. You could ask yourself, why is it called marine cloud brightening? And why can't we do this on land? Well, one issue on land is that you're just too polluted. You have too many aerosols competing for that water vapor. So hence the marine cloud brightening.
Oh, Andrew.
The jet fuel particles that you're talking about, so they come out and they're black, so they would probably have a heating effect. And then in dry air, if they float around and don't form water droplets, then they remain black and that's for warming. But in wet air, then they form water droplets, and then eventually those water droplets will grow and fall out. So there's quite a complicated relationship between the albedo and the properties of the material. So does it have a net warming and a net cooling effect? And can you speculate as to where in the world there might be more or less radiative forcing and which sign it will be?
Yeah, well, globally as a whole, for aerosols, we don't know that answer. So if you look at, you know, the scientific consensus and IPCC reports, we know that aerosols are roughly the third in the terms of magnitude of radiative forcing at CO2, methane, and then aerosols, but we don't know the sign. It is the error bars are both positive and negative. So that is at a global level. You know, we know better in certain situations. So in contrails specifically, we have better estimates of that. So by far the radiative forcing in a contrail is really around the droplet that forms. It's not the black carbon. That is not true for forest fire soot or is more complicated. We don't know the answer as well for forest fire soot or other major soot. The forest fire soot it tends to be what dominates at a global scale. Unfortunately, where I live now, California, of course, it really dominates. And that's a very complicated relationship that we just don't know the answer to. And just to kind of give you kind of a little insight into why it's so complicated, it has a lot to do with where that particle resides even within the droplet. So you can imagine that as a droplet forms, if that particle is phobic to whatever that liquid is, it might reside at the surface and largely have about the same radiative effect as it would otherwise. If it resides in the middle of the droplet, if it's philic, it likes that liquid that has grown on the surface. Up at small sizes of droplet to particle, you get a lensing effect, and the particle actually acts bigger. It absorbs more light than it would without the liquid. So light rays actually get scattered into it. Then it gets big enough, and the light rays miss it, and so then it's net cooling. So it's a complex relationship. Yeah, and so we've got good indications in some narrower instances, but we can't say globally what aerosols do collectively.
But there was a thing after the Australian bushfires at the end of 2019. All this smoke went over to New Zealand, and New Zealand got cooler. Is that something you have any? No. That's
No,
right.
I don't know anything about that specifically. Yeah.
Right. Question. We've got to have at least. Oh, okay. Andrew, you can be the token least school student.
Thank you, Hugh. Instead of filtration, has anybody looked at possibilities like mechanical separation, such as centrifuges?
Do you want to say something about filtration?
Or is it desperately inefficient?
As far as I know, I don't think that anyone's looked at different options. I think that one thing that's worth saying is a key benefit of marine cloud brightening being implemented in the way that we're suggesting is it allows for a targeted approach. So, for example, I know that another big thing that the Centre for Climate Repair is working on is talking about thickening Arctic ice, and there have been barriers to implementing marine cloud brightening in some ways because there's kind of governmental issues. And so the idea of using it in a targeted way is very appealing. So when you have kind of a single boat spraying these droplets, it's much easier to manage. It's something like a centrifuge, I think, just like thinking off the top of my head, would probably might poses more complicated issues for putting that system onto a boat and onto a kind of relatively small boat, rather than a filtration system, which is in itself is quite like an elegant system, because obviously the feed that you need, the raw seawater, is what you're surrounded by.
Very good. Well, look, we need to wind up. So just a big round of applause for our three speakers. Thank you very much. And just to say a couple of little announcements. We'll try and keep you posted on what things are going on around the world. Today at 5 o'clock, there's a webinar on Greenland and how it affects how the melting ice affects the planet. That QR code should get you there. And also tomorrow, 9 o'clock in the morning, there's a session on SRM research. And then our next session in here on ice thickening. What would happen if we could make more ice? And then the fourth session that's in 2 weeks' time, and in 4 weeks' time, capturing greenhouse gases. Then our conference, Arctic Repair, at the end of June. Anyone interested to be student helpers, then let us know, and you can follow us on our mailing list with that QR code there. Now, next time we might even have some mugs to give away. Oh, look at that nodding! So we've got a bit of what do they call it? Swag. There we go. So good. See you in a couple of weeks' time. Thank you very much.